Today we will cover 16.8 and 16.9 Stokes theorem and divergence theorem. They are optional, which means it won't be tested. We have mentioned the Stokes theorem a few times before. Now let me formally present it. If you are given a vector field and a closed curve, then the integration along that closed curve would be same as the integration of the curl across that surface. Suppose you have a surface S and the boundary called C can be chosen as clockwise or counterclockwise, and we have to choose the counterclockwise on the left side. And when you say this ds, it has a direction, and this n, instead of the other way, instead of the downward one, it should be chosen consistently with this counterclockwise direction by the so-called right-hand rule. So in this picture, if you curl your right fingers along the C, the counterclockwise direction, then you will see your thumb pointing in the n direction. So this n should be chosen in such a way. Otherwise, you will you will be off by a -1. Okay, so this is Stokes theorem, and I'm not going to prove it because it's kind of hard. And actually, I'm going to just give you one or maybe two special cases. Okay, first special case: if our our vector field happen to be as simple as just P and Q and no R, then, and it's also only about X and Y, so it's a completely two-dimensional field, right? Like that. Oh, sorry. You have an X and Y. It's a 2D field. And our curve is also 2D. So the left-hand side is just what we have in the green theorem. Right? Let's see what do we have on the right-hand side. If you take its curl, then you will see its curl equals I, J, K, partial X, partial Y, partial Z, P, Q, 0, and then you will see this will give you Q is independent of Z, so it's 0, and P is independent of Z, so it's also 0. You only have the last term, which is Qx minus Py. So, and if our C is chosen to be counterclockwise, then this ds must point upward, which means this n equals k. Then your integral on the right hand side equals s, and this is 0, 0, qx minus py times k and ds, and this s is just the interior of this c, so it's just the same as dA. So when you do the dot product, you get qx minus py dA. And that's exactly what we have in the Green's theorem. So you can see Green theorem is just a 2D version of the Stokes theorem. Okay. And now let me tell you a little corollary of this. Suppose you have a curve, let's say curve C, and let's say it's in the 2D plane. So we know the interior is S, right? So we know the integration along C equals the two-dimensional integration of the curl of F across the surface, right? Now I change this S to be something, let's say this is a circle. I make a sphere on top of it. And this is still C. Right, I call this S1. And this S1 is a totally different surface, but it shares the boundary with S. They're both C. And now I claim if I compute the curl across this new surface, then it's a totally different integral, right? Because this is over a different surface. But I claim it's the same as before. Okay? And why that? Because according to the Stokes theorem, they are the same because they are both equal to the integral along the boundary. And what is the boundary? The boundary is C. Right? You know, it's C here and it's C there. They have the same boundary. So Stokes theorem tells us that the integration of the curl across the surface is independent of which surface, so long as they have the same boundary. That's quite amazing. Okay, because you know this boundary, I mean this S1 could be much more complicated, but still we can say the integration is the same. All right, and that's it for the Stokes. The more interesting theorem is the divergence theorem. And divergence theorem says if you have a 3D domain, let's call it E, and you take the divergence of a vector field and integrate in the domain, then it will be the same as the boundary, the entire boundary, which is a surface, entire boundary of E, which is a surface we call S, the outward, this is outward. So we choose the outward direction to be the, you know, the direction of the ds. So this is called outward flux, and this is the integration of divergence. And actually you can see why it's called a divergence, because if the outward flux is positive, then it means there's something outflowing, so that's why it's divergent, because you know, if something is leaving this region. And this theorem is very useful in physics. And here I just give you a few retrospect examples. Remember last time we showed, we have two examples. One is an integration over a domain like that, which is a boundary. This is E, and this is bounded by y equals x squared plus z squared, and y equals 1, right? This is the origin. So that's the region, and we found that this equals 0. Remember, first I thought it's pi plus pi, then I figured out it's pi minus pi. It's 0. And I can tell you why I know it's 0. Because it's an enclosed surface, so by the divergence theorem, this should be equal to the divergence of the field integrated over this volume. And the interior is just this 3D domain, but what is that? The divergence means the derivative of that is 0, derivative of that is 1, derivative of that is -1. Oh, okay. Derivative over x, over y, over z. And add together, what do you get? Is 0. So the integration of 0, of course, is 0. So that's why it's 0. Alright? Now let's see the other one. The other one is a cylinder. This is z equals 0. X squared plus y squared equals 1, and z equals 1 plus x, right? And this close the surface, I have this y, x, z, ds, and 0, this s, I said in the end it's equal to pi. And I know it's correct because I can predict. This is a closed surface, so it's same as the divergence of this over the volume. And what divergence of that? The derivative. Okay, this one equals y x plus x y plus z, and that equals 0 plus 0 plus 1 plus 1. So that equals 1 times dv. So it's just the volume. Okay, what is the volume of this guy? Well, this is the center of that ellipse, and this is the height is 0, this is the height is 2, so the average height is 1. So the volume of this guy is same as the volume of this cylinder. And the volume of the cylinder is pi times r squared at the base, and the height is 1, so that's pi. So I know why the volume should be pi, and the integral should also be pi. Okay, so you can see if you have an integration over a closed surface, divergence theorem can really help. It can get your answer much easier. Okay, I think that's it for all this semester, and we will have a review in next class, and we will have the exam after that. Okay, thank you.